my talk by thanking MCQST for having me here today. It's a pleasure to be here. And also I wanted to say I'm really grateful for being here because what really makes MCQST an excellent cluster and stand out as an excellent cluster is the community. I mean, the level of mentoring you have from bachelor to postdoc level. So if you're a student here in the audience, just take advantage of that because it's really, really nice. So yes, for those who don't know me, my name is Viviana. I work with Professor Kai Müller and Professor John Finley at TUM, at Walter Schottky Institute. And today I'm going to show you a couple of results we got on SiV color centers in diamond and MV color centers in diamond. But first, I would like to give a brief introduction and tell you what do we care about these color centers, why. And why do we want to work with this is because we want to actually build a quantum network. And there are like three big promises of quantum networks out there, three big motivations, if you would say. The first one is to have long-range secure quantum communications using quantum repeaters that are diamond-based. The second one could be do some distributed quantum computing, so you know that we will have like quantum computers and we will want to interconnect them. And the first one would be to have distributed quantum sensing and metrology. So for instance, here I'm showing an example of how synchronizing a quantum clock network could look like. So my main field of research is group 4 color centers in diamond. These are obtained when you have, for instance, a silicon, tin, or lead vacancy in the diamond lattice next to two missing atoms in the carbon lattice, in the lattice along the 111 direction. And when you do things correctly, then you have an optically active defect with a zero phonon line at 1.68 electron volts or 737 nanometers. Now, this defect is it's subject to a very spin orbit coupling, so you have an electron here, but actually the ground state gets split into two, and also the excited state, and the splitting is 50 gigahertz and 250 gigahertz on the excited state. Now, this is without applying a magnetic field, and you can for sure use these two states in the ground state as a qubit. You can use this orbital degree of freedom, and then you will have a coherence time of about 10 nanoseconds. But if you apply a magnetic field, then you can split the spin state into the up and down configuration and then use this guy as a qubit. And then you will find out that you have a coherence time of about 10 milliseconds. And as Paola said just before me, what is nice about diamond is that you have actually access to register. This is nuclear spins in the diamond. So for instance, if you get lucky enough, and if you are sitting right next to a carbon-13, then you can have access to the nuclear spin qubit and store your quantum information there, achieving coherence times over 200 milliseconds. So this is why we care about these color centers. And just briefly to say that diamond could be a nice candidate to build a quantum network, I'm going to show you two reports of diamond-based quantum repeaters on metropolitan scales. So the first one was done at TU Delft using MV color centers in diamond. There they have like two diamond nodes physically separated 10 kilometers. The quantum information ran over 25 kilometers of fiber. Of course, they needed a telecom conversion up to 1.5 microns because the zero phonon line of this guy is 637 nanometers. And the protocol they used is very simple. So you can think of this guy as a lambda system. And then you can have the two color centers emit photons at the same time. And then you can do the optical interference using a beam splitter. And then you can have entangle the spin states of the two MV centers. Now, the second implementation was done by the group of Misha Lukin at MIT and in Harvard, sorry. And there they were using SiV color centers in diamond. The nodes were physically separated 3 kilometers. The quantum information was being transmitted along 35 kilometers of fiber. Again, they needed these telecom conversion into 1.3 microns because the zero photon line sits at 737 nanometers. And here the protocol looked a little bit different. So they had like a reflection-based time beam protocol. So the SiV, they had a single SiV sitting in an optical cavity, and then they had a very strong interaction between the optical cavity mode and the spin defect here, such that they were sending single photons into the cavity, and provided that the single photons got reflected or transmitted, they could achieve this spin-photon entanglement with spin-up or spin-down configuration. So to start my talk, I will show you to see what we will see today. Actually, we have 3 research areas in our group. The first one is about the charge state environment of our group 4 color centers in diamond and how to control it and pacify it. The second one is developing spin control techniques at millikelvin temperature, and then we are also investigating a little bit of spin optomechanics in this, with these color centers in diamond. I will show you results from the 2 first areas today due to time constraints, but we can also discuss the third area as well. And so let's start. So what about the charge state environment, and why do we care? And here I'm going to rely on the talk of Paola just before me. It was really nice. She did a very nice introduction to explain how we buy diamonds from element 6, and these are very pristine lattice, but then we just shoot the diamonds with these defects to create the color centers. And by doing so, we create a lot of damage in the lattice. And we create, this damage can actually trap charges and actually induce a lot of electric noise in the surrounding, in the vicinity of the color center, which turns out that it induces a lot of optical decoherence. So here I'm showing you a couple of examples on how this works. For instance, if you have an NV center in a nanopillar, here what they are measuring is the zero photon line as a function of time. And you can see that 2 bad things are happening with the optical coherence of this center. The line is not only flickering, but it's also moving around. And this is something undesirable for the applications that I discussed at the beginning. So this happens with NV centers. This also happens with SiV color centers. So here you can see how the line is going dark and bright. And these 2 examples are taken from papers that were done with color centers in nanopillars. So you in the audience could argue, well, Viviana, these are close to the surface, so there you have a lot of charges and traps. But this also happens in the bulk. So here is an example of tin vacancies in diamond, and you can see a lot of optical decoherence as well. So quick recap. Last year, I showed some results with, that Manuel had published, where we were trying to get rid and pacify this charge state environment by putting some gold electrodes at the top of our diamond and addressing these SiV color centers using off-resonant excitation. So here is how the PL of a SiV looks like when you have a green laser shot at it. You can see 2 lines here and 2 lines here that are not resolvable because we are measuring with a normal spectrometer. And what I showed is that by tuning the voltage across these electrodes, we could switch the emitter on and off. And in order to explain this result, what we learned, we had a take-home message that is, we need to shine a green laser before even starting to address the spin on our SiV diamond color center in order to fill all the charge traps that are surrounding our color center and then start playing with the spin. So this was the take-home message from last year. What did we do in the meantime? Well, we started addressing our SiV color center in diamond using resonant excitation. And we are actually doing this because we want to do an optical pumping scheme to optically initialize our spin state. So for instance, we take a laser and we shine it on the C line, and then we can initialize our state in the upper manifold of the ground state. And if we do this and just measure how the PL looks like as a function of time, as I'm showing you here, what you can see is this is the green laser initializing our SiV. Then we stop the green laser and we start shining our resonant laser on the C line. And what you can see is that the PL quickly decreases until it's 0, meaning that no matter how much power we use, after a few milliseconds, we just lose the electron. So we cannot actually play with the spin for long times. And what we discover is that this happens when we don't apply a voltage on our sample, but as soon as we apply a voltage, we can counteract this effect. So here I'm showing you a few traces of what's going on. At 0, we have no PL at all. 10 volts, we have a strong decay of our PL. And for 50 volts, we can have the PL emission through the entire time trace. So we wanted to understand what was going on here, and the first thing Manuel and Nori sitting there did is they developed this toy model, which is just solving for the rate equation model. We have the SiV minus ground state, the SiV minus excited state, and the dark state. We are driving this transition here, and at some point, our SiV goes into the dark state where it doesn't emit any photons anymore. And indeed, they were able to extract from the experimental data these two curves which refer to the conversion rate. So this is in a log scale. The dark to bright conversion doesn't change that much, but the bright to dark conversion process, the rate is changing a lot, and it has a minimum around 50 volts, which is what you can see here in this trace. So by applying 50 volts, this magic potential, we can really decrease this conversion rate. So what's going on? In order to understand what is going on microscopically, we need two pieces of information. The first one is that this decay rate that we observe is linear with the laser power that we apply, meaning that the conversion process is a single photon process, because this is a linear slope. And the second thing that we need to learn is that after we initialize our SiV on the bright state, it doesn't matter how long we wait. When we come with our resonant laser, we always find it in the bright state. So it's always emitting photons, here, 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 and then decaying. So we can wait. And this is telling us that actually the laser driving the conversion between the bright to the dark state is the resonant laser. So yes, so this is the SiV band structure now in order to understand what's going on. I have plotted the valence band, the conduction band, and the 4 SiV states with all of their electrons. When everything is working fine, we come with our laser, we excite an electron from the ground into the excited state, then we end here, and then we get a photon out. Perfect. But this is not the whole story, because SiVs are actually very close to the valence band of our diamond, and these EU levels are actually resonant to the valence band. So if you look at the DFT calculations on how this confined state arises, they have a lot of contribution from states actually coming from the valence band. So what can happen is that we are in the excited state, but then this guy just drifts away. So we lose a hole or we gain an electron, and then we end up in the optically dark SiV2- state, which we cannot sense with optics, of course, but it also is a state that has spin 0, so we cannot see it, and it's dark. So how come the voltage can help us prevent the whole diffusion? Well, what we think is happening is that we are actually modulating the binding energy of our SiV minus, meaning that what we are actually doing is changing the distance between the ground state of the SiV and the top of the valence band. So I'm not claiming that this is a direct effect, because, of course, this would be too much. I'm claiming that the overall effect is the change of the binding energy of the SiV2-, and this is essentially induced by two things. So the illumination history of the site that we're applying, how strong we pump with green laser before we start measuring, and what is happening at the electrode. So you can imagine that if you are sitting next to one of my gold electrodes, you will have, it's a Schottky diode, and you will have a strong depletion region. So around my defect, I can have a lot of electrons or holes, and this in turn will change a little bit the binding energy. So what we did here is just apply a simple toy model to actually calculate the ionization time of our defect as a function of the voltage and the binding energy of our defect. And indeed, we found out that this could be a plausible explanation of what we observed. So here in black, you can see we highlighted some curves that would correspond to the experimental timescales that we have measured experimentally. Now, actually pinpointing where we are sitting with binding energy and voltage is not so simple anymore because it depends on which defect we are looking at, and each defect is indeed a little bit different because the strain actually modifies the position of the ground state with respect to the valence band, and every defect has a little bit of different strain history, but we find here a plausible explanation of our experimental data. So this brings me to the second topic that I wanted to discuss with you today, which is the spin control techniques that we are trying to implement in our blue force. And I figured this would be a nice occasion to show you these results because we are in a quantum sensing session. So the question is, Viviana, why would you take NV centers which were good at room temperature and actually cool them down to millikelvin? And I tried to come up with an answer for that, so I have this slide for you. The first thing is we know that NV centers are good for quantum sensing, and if you try to actually use them at millikelvin temperatures, you can actually sense cool stuff. For instance, here what I'm showing you is a report of sensing of the magnetic field of an aluminum microdisc, as you can see here. So this is the optical image of an aluminum microdisc, and what the authors did is actually measure how it's the magnetic field at 350 millikelvin using ODMR techniques. And what is cool about this is that you can see here the magnitude of the magnetic field. It goes from yellow to purple, and these are actually vortices because the aluminum is a superconductor there, and they're actually taking pictures at vortices, which I find personally really cool. But coming back to my motivation at the beginning and also to the talk that we had before from Paola, they're not only good to measuring the magnetic field that it's outside of the sample in this case, but also to do quantum sensing inside of the diamond. So here I brought two examples of quantum sensing done with a single NV center of the environment. And in the first example, what the authors were doing is actually figuring out how many they were actually coupling their electron in the NV center to nuclei spins on carbon-13 atoms that were found in the lattice, and they found that they could actually have an 8-qubit register. So here you can see the measurement where they can couple it to each of these nuclei spin separately, and they can store quantum information in each of them. And more recently, you can find some crazy stuff here. So using a single NV center to image a qubit register made of carbon-13 atoms, and you can find up to, the authors find up to 50 of them, and here you can see the spatial location with respect to the NV center they were using. And here you can see black lines that are thicker and thinner, and this amounts to the coupling strength they found. So it's interesting because you can also do this sensing inside, and you can find qubit to find if you can have a register. Now, these two examples were done using single NV centers. In this case, they had like a NV diamond tip with a single NV center, and this was a bulk diamond with a single NV. We are doing our experiments with a sample that has many NVs, so it has a 1 ppb concentration of NVs, and we want to figure out what happens then. And a good reason to go in this direction is because when you have NV centers everywhere, you can go from a scheme where you have a scanning tip to actually measure the magnetic field. Of course, this gives you high resolution and coverage, but it's a little bit slow, into an ensemble in which you can have fast imaging because you are measuring a lot of them at the same time, and you can take pictures faster. So we wanted to see what we could do with an ensemble of MV centers at millikelvin. So I'm going to skip this because Paola did the introduction, so now I'm working with an MV. It's a spin-1 system. We have the free states in the ground state, the free states in the excited state. And yeah, what we can do is apply off-resonant excitation, and then due to the intersystem crossing, you will end up in MS0. And then if you apply a microwave field, you end in the dark state. So just by measuring how many photons you get out, you can just figure out if you are in 0 or -1 or 0 or +1. So I'm a spectroscopist, so the first thing we did in the lab with Toby and Mohammed is actually see how the spectrum looks like. We went from a very bad spectrum. Here you can see a big photon SiV², divide-Waller factor about 30%, into a very nice zero photon line here with a much higher divide-Waller factor because we were at millikelvin temperatures. And then the first experiment we did is, well, we tried to figure out whether we could see OGMR, and indeed we can. So we just initialize our spin state on 0, and then we swipe the frequency of a microwave, and then we read out the state. And we did this as a function of the magnetic field orientation between the NV axis and our magnet. So here I'm just swiping the angle, and you can see all sorts of lines. And because we are working with that ensemble, we expect to see 6 lines due to the fact that we have 3 possible NV orientations. And yeah, we can simulate this very well with a very easy toy Hamiltonian, so we think, okay, we can understand this. And if we zoom in as in one of these resonances, we figure out we could also see an ensemble of the ensemble of nuclei spin actually affecting our resonance. So here you can see the hyperfine coupling to the nuclei of nitrogen-14. So the next thing you can do is just a Rabi contrast. So you just swipe the time in which you apply the microwave, and you can see very nice Rabi oscillations. And then we did our first experiment, which is just a Ramsey contrast. We initialized at 0. We just write a superposition between 0 + 1. We let the system evolve. Then we put it back at 0, and we read out whatever is left. So what you would expect from a theoretical point of view is just an exponential decay of a system, because you just write 0 + 1, let the system evolve, and then put it back at 0, and you read. And you're losing coherence, so what you would expect is that the vector on the block sphere is just reducing its magnitude from 1 to 0, but we actually see oscillations. And as was explained in the latest talks, these oscillations are arising due to the fact that we are coupling the electron with the nuclear 14 spin. So in this case, the frequency of our microwave is set here on the middle, and we have this hyperfine coupling with nitrogen-14 here and here. And these two are in phase and are giving rise to a coherent signal, which is the oscillation of the electron due to the hyperfine coupling, which is kind of cool to see. And yeah, so we can go one step further and run a hang echo or a spin echo experiment. And yes, as it was explained before, we just initialize at 0. We apply pi-half, we write 0 + 1, and then we let the system evolve, but it will have a lot of decoherence because we're working with an ensemble, so we just apply a pi shift in order to counteract that dephasing, and a pi-half again to read. And again, you can see that now this is at room temperature. We can see oscillations, of very small frequency and a decay time as well. And these oscillations are now arising to the coupling with an ensemble of carbon-13 atoms in the lattice. So at room temperature, we could see 3 of them. Maybe there are a little bit more, but you can see the strong decay. We did these experiments also at 400 millikelvin, and then you can see this is the same experiment as before. It's just with a different time scale here. We can see these oscillations arising also from the coupling to the carbon-13, and now we see a lot of them as a function of time. We see many revivals of the coherence of the electron spin as a function of time whenever the motion of the nuclear spin is matching a multiple of the electron spin. And isn't it really nice to see? We are still trying to understand how to control this and how to characterize this better. These measurements are fresh from the lab last week. And the reason why I stopped measuring here all of these revivals is because, last week there was a thunderstorm at Garchin, so our magnet quenched. But we will continue to see how long we can push this, how many revivals of the coherence we can see as a function of time. So right now, I'm not able to claim what is the coherence time, but we think it's about 1 millisecond, so we're going in the right direction. So this brings me to the end of my talk. I hope I was able to convince you that we can a little bit understand and pacify the charge state environment for group 4 color centers in diamond, and that we are giving our first steps into doing like the full spin control of MV color centers at millikelvin temperatures. Well, I would like to also thank John and Kai for their support. Martin is a nice collaborator, which is teaching us how to make all of these sequences work. Tim is giving us support with the nanofabrication side on our diamonds, and the big thank goes to my students who are really the ones who are measuring and fighting in the lab to have nice measurements. So thank you very much.
Thank you, Viviana. Great results, great talk. Are there questions? Hans again.
Thank you for your talk. I have a question regarding the temperature of your experiment. So you state that you operate in a dilution refrigerator. Can you tell us anything about the actual temperature of the spin system?
Yes, that's a huge problem. We have indeed a couple of sensors there, but we're still trying to figure out what's the actual temperature. It's hard to figure out what's the actual temperature using the ODMR contrast, because the contrast as a function of temperature has a huge variation around 50 Kelvin, but then when you go into lower temperatures, it's just flat, so you cannot actually use that as a calibration for what the actual temperature is. What we are doing at the moment is being really careful about the duty cycles of the sequences. So it's taking us longer to measure because Toby there is just applying very, very small duty cycles to avoid heating the sample. But indeed, this is a problem when you work at millikelvin. Both the laser and the microwaves are heating the sample all the time. Yes. We don't know what the actual temperature is. We think it's very low, but it could be more.
Okay, I think for time reasons we move on. Let's thank both speakers again. And